So I will begin. First of all, thank you for the invitation. And if you have any questions during the presentation, you can just interrupt me and ask your questions. I will try to be brief about the presentation. And as Professor Özcan said, I will talk about the landscape of academic literature in quantum technologies. This is a recently published paper of ours. And I'm from Middle East Technical University in Ankara. This work is kind of a collaboration between the physics department and the science and technology policy studies department. And I'm also a member of the Q-World and a founding member of Q-Turkey. The outline of the presentation is of the following. I will very briefly talk about the background of this work, followed by the methodology and what are the bibliometric tools, the dataset, keyword analysis, burst detection, core corpus, and discussion. And the background of this work is actually, to understand what the background of this work, we need to understand what bibliometrics is. It is the field of study of the academic literature. And by academic literature, I mean the body of work of physics, chemistry, any field that you can think of. You can study those fields through bibliometric means. And the origin of bibliometrics is actually rather old. And by old, I mean it goes back to 1960s and to this just one guy called Eugene Garfield. He kind of originated the field, and the idea behind the field was this: the number of journals are increasing, and universities needed some way to find which journals they need and which journals they don't need. So Eugene Garfield came up with the idea of counting the citations of these work, and this is actually one of the first way of rank ordering the journals. So all the things that we are dealing right now as academics, like H-index, impact factors, the Q1, Q2, all those stuff, they actually go back to 1960s and 1970s, and the desire for the libraries to decide which journals to buy. But the field has progressed rather rapidly after 2000s, especially after the development of computational models. And now, instead of counting the citations with hand, we use certain software tools and certain structured databases. And so Arsev Aydinoğlu is my co-author in this work, and he is also my instructor for bibliometrics. And we decided on this study because of his previous work in NASA Astrobiology Institute. So I will very briefly talk about the methodology and the bibliometric tools. We used Web of Science. There are actually two well-structured data set sources for this kind of work. One is WOS, Web of Science, and the other one is Scopus. You can use either of them. Web of Science has fewer journals indexed. I mean, the thing that we know as the Science Citation Index is what Web of Science index. And Scopus has more journals, but since it has more journals, the quality is a little bit lower. So what we did for this work is, initially we needed to determine a sample size and formulate a search query. And we initially formed the query ourselves, ran some analysis, sent it to experts, got some feedback, created a new query, rerun our analysis, and finally asked our experts whether this analysis makes sense or not. And also we used the highly cited article set provided by Web of Science depending on your search query. And the software tools that we used are WOSweaver and SciSquare tools. Both of these are open softwares that you can use. You can just go to their website and you can read the manual and you can start using them. So the initial search query of ours was like this, and the final search query after the analysis and expert opinion feedback was like this. So initially, with the first query, we ran the analysis in 13th of March. We collected the data on 13th of March in 2019. We had 41,000 articles and proceedings. And after the previous, intermediate steps, we finally collected our final data set in 6th of June 2019, and we only focused on articles. And there was around 50,000 articles. And we curated the set, which means we got rid of articles with 0 citation or 0 references. And afterwards, we had 42,500 articles. And there were there were 495 journals with 5 or more articles in our dataset. So the reason I am giving you this date is if you go to Web of Science and use this search query, for this date, you will exactly find the number of articles that we have found. So you can replicate this by yourself. I mean, the number of articles maybe will change just a couple because maybe there's a retracted article. But that's it. Other than that, this analysis is entirely reproducible. And that is one of the good things about bibliometrics. So the number of articles in the field has been increasing rapidly, and here you can see the graph. And following 2000, as you can see, the trend is very steep and upward. And we checked the co-authorship of this field, and here you can see that this is for the full list. The red line, the blue line is for the articles with less than 50 authors, and this green line is for articles with less than 10 authors. And in all 3 cases, you can see that the average number of authors per paper has been increasing steadily. So the field has been becoming more collaborative, and as of 2013, the mode of number of authors is 3, which means most of the papers here have 3 authors. So single author papers are very old-fashioned now in the field, and usually the papers are the outcome of 3 persons' work. This is from our initial keyword clustering with the first query, and you can see that it is not, it seems reasonable. And after our feedback and the second and final query, this is the final version of our clustering. And this is the 60% version, which means we only use the top 60% of the keywords and the relation between them. So here you can see actually 3 clusters. The red cluster is, we thought the red cluster as the physical hardware cluster. You know, the more experimental science, more experimental physics, and more implementation-oriented works form a cluster in themselves. And here in the blue cluster, you can find, by the way, the colors are meaningless. You can change the colors. This cluster is basically consists of quantum communication, key distribution, single photon sources, single photon detectors. And this green cluster actually consists of quantum computation and quantum information theoretical tools. And we can actually see that if we use all the keywords and the relationship between them, all the clusters come more closer. But you can see that there is a 4th cluster emerging. And what happens is actually the quantum information theory cluster separates from quantum computation. And here you can see that this cluster is more related to like concurrence, quantum discord, entanglement dynamics, phase transition, and kind of like emerging topics like quantum thermodynamics. So if we use the clustering of terms that are occurring more than 200 times in the total set, we can find three main sets, three main clusters. And if we increase our precision, we can find other clusters as well, but these three are actually enough for our analysis. And this is followed by something called burst detection. So we used Kleinberg's burst detection algorithm. It identifies sudden increases in the frequency of words. So it is not just frequency analysis. It's kind of taking the first derivative of the frequency analysis. It is not exactly that. You can check the paper, but rather than using simple frequencies of the occurrence of words, the algorithm employs a probabilistic automaton. So it's not just frequency analysis. You can check the paper. And here in the chi-square tools, there is this parameter called the gamma parameter. Again, the name doesn't matter. If you increase the parameter, the constraint on the burst is lowered, which means you can see more words. If you increase the parameter, you will only see the higher bursts. And with respect to time, this is the lower parameter burst analysis, the result of the lower parameter burst analysis. And here you can see the initial burst starts at 1995, which is not a surprise. That's the year Shor algorithm came out. And it is quantum computation, and it has been a quite long burst. And similarly, like entanglement, teleportation, quantum computing are bursting. This is followed by cavity QED, entanglement, theory, optics, discord, and correlations. So as you can see, the bursting topics are evolving. And if we check the higher parameter list, these were the keywords or the topics that have been still bursting. So they are still hot topics. As of moment, we collected the data set. So remember that our data set ended in 2019. These topics were hot topics in 2019. Maybe they are still hot topics. We don't know that. But if you run the same analysis again, you will find out. And as you can see here, like quantum image processing, networks, annealing, steering, ADS-CFD, quantum metrology, open quantum systems, all of these are really recent and let's say interesting fields of study. And okay, we have 10 minutes. So just because I didn't, I want to double check the algorithm. And so remember that when here the burst ends, we don't know whether the burst actually ended or the field faded away, or whether it became mainstream. But here you can see, for example, for quantum teleportation, the field became mainstream. Like it is stable enough. I mean, it is fluctuating, but it is stable. So quantum teleportation arises in these kind of part, and then it became study. But here you can see, like quantum simulation, it bursts starting from here. And again, quantum coherence, it is bursting. Quantum annealing, it is bursting. And you can see them here as well. And remember the huge burst in quantum computing. So here, I don't know what happened this year, but you can see that something happened with quantum computing. And the highly cited articles list is a list of articles provided by Web of Science that are not just the articles that have the highest number of citations, but the articles that have been getting those citations rather fast and rather in huge volumes. So what we did was, out of these 808, we identified 34 works, let's say, which had over 30 citations in the set of highly cited articles. So we use them as a core corpus. And you can see the full list in the paper, but we checked whether these highly cited articles or these core corpus have different citation dynamics between this highly cited set and the entire curated set. And here you can see that the most cited work is Nielsen and Chuang, which is not surprising. I mean, for both lists, Nielsen and Chuang is cited way more than all of the other works. And for the entire literature, you can find that the other highly cited articles are like Bennett's, Eckart's, Gisin, and EPR paper. But for the highly cited set, which means for the really recent and high cited articles, they are citing works like Kimball's Quantum Internet paper or Walraff's Superconducting Qubit paper, Nayak's Topological Quantum Computing work, and Torodetsky's Quantum Measures. And this is a country level analysis. You can see that China is producing the most amount of papers. This doesn't mean all of them are high quality, but in terms of quantity, China has most of the papers, followed by US and followed by UK and Germany. And if you combine the entire European Union, even without UK, almost all three main regions have similar amounts of academic papers. And here you can see a collaboration map of these countries. You can check this in the paper as well. And Egypt is actually here with China. And this is an institution level analysis. So here again you can see Chinese Academy of Sciences have most of the papers. This is also because in China, most of the academics or some of the academics that are working in other universities have also Chinese Academy of Sciences affiliations, which means there are double counts in this list. But even in that case, the Chinese Academy of Sciences has an overwhelming institutional advantage in this institution level analysis. And here you can actually see that co-authorship analysis of organizations with more than 150 published articles. You can see that the Chinese institutions are clustered together. So I think this is Taiwan, and this is the Japanese institutions. But here you can find, so this is most of the European institutions. Here you can see Canada and Australia. And here you can see the US collaborating with Denmark and Switzerland. And also here is a very small cluster for the Russian Academy of Sciences, and here for Singapore. So this discussion, what can we say from this work? We can say that using bibliometric tools to examine the field of quantum technologies yields valuable insight. You can actually see what is bursting and what is popular in the field. You can also say that bursting topics evolve away from straightforward quantum computation into more diverse areas, like quantum image processing, quantum steering, ADS-CFD. And also you can say that China, the US, and EU have similar sizes of contribution to the academic literature. So you cannot say that there is a winner of this race, or you cannot say that, you know, the literature is mostly from US or mostly from China. It is very evenly distributed. And also we can, just by looking at the outcomes, we can say that Chinese institutions, or more mainly Asian institutions, tend to collaborate with each other more heavily compared to their European and American, let's say, counterparts. Here are some of the references. You can actually find our papers in the International Journal of Quantum Information. and I thank you for your attention.